All right, good morning. Welcome back to 128A. So I don't have too many announcements. I guess I could ask you if you have questions, but remember, one group has already had a section this morning and presumably handed in their homework. So unfortunately, we shouldn't discuss too much homework. It has to be done by Tuesday. I think it's too bad that they put the lectures and I think last time I taught it, the sections were maybe Wednesday and I taught on Tuesdays. But having said that, any general questions? Are you guys doing fine? How did it go with the morning group? Yeah, question.
I just have a general question about turning in MATLAB code.
Okay.
How would you, do that? Do we just print the function and the command?
Okay, so MATLAB code in general. So there will be 4 big programming assignments, right? And then we could talk a little bit more exactly how to hand in that. But yeah, basically you would print it you would write a little report for those. Homework is rarely actually explicitly asking for MATLAB code. I'll think about whether it does it or not. And we'll talk a little bit about, when I show you my MATLAB code, we'll talk about whether you can use it or not, because you can, but how much you should document. But I think there are very few homework problems saying write a MATLAB function doing this, right? So that's less of a problem. For the programming assignment, yeah, you write a little report. Like, here's the function you asked me to implement, cut and paste, right? That's typically how you do it. So I'll discuss that more when we come to programming assignments. Otherwise, the homeworks are like usual calculus, anything homework. Just write them up in a nice form and hand them into your GSI. All right, yeah?
You mentioned that this is being videotaped?
It's not videotaped, it's audio taped only. So yeah, it might. So I think it's webcast.berkeley.edu. I haven't looked. I'm going to look it up and look at the link. So yeah, and there's also a Berkeley YouTube channel, and it's on both places. So you can probably find it easily. But it's really just the audio and I think the screencast. But as you see, the way without the Blackboard, it's going to be hard to get the context. More questions? Looking at the schedule, of course, there's a new homework due in a week from now. And just reminding you that, so next Tuesday, that will be due, and there will also be a quiz done on all these problems. And I don't know if you feel that, I'm thinking you guys might feel that it's not a lot of homework if you compare to like a calculus course or something. And that's because, you're a little too mature for this homework, I think. Many of these homeworks are really just routine. I signed a few of them. If you feel when you're doing these, which am I thinking of? Maybe 1.1.14 was the routine type Taylor polynomial stuff. If you feel you need to practice it more, just do a few extra ones. It's all about learning, right? So, especially in this section, many of these problems are just routine. The book, actually, they are what they are. Also, you will struggle with your programming assignment soon. I'm just giving you a break now in the beginning to learn MATLAB. But you'll have plenty of work. But yeah, I just didn't feel that there was that many problems in these chapters that were interesting. So hopefully you can see that as a good thing. Also, you just have one section a week. So if I bombarded you with, for calculus, I assigned 25 or 30 problems per week. That might not be that much time for that. But the good news is that hopefully you don't think it's too overwhelming, at least not at this point. Typically, it will be 2 or 3 sections, as you see, with homework every week. Yeah.
Will the quiz cover just this week's homework?
No, both. Quizzes, I want them to, yeah. So it will typically go. Actually, talk to your GSI exactly what they want. Some GSI I know, from my previous calculus teaching experience, they like to actually have them a little bit accumulative. Ask your GSI if they want that. I didn't really strictly tell them what I asked. Although the way I arranged it is pretty obvious that I'm thinking that on the quiz next Tuesday, it will be covered, the homework from number 1 and 2, right? So, and then pairwise like that. But check with them. They decide more. I leave it pretty free for them to decide on how to run the section in that sense. Yeah.
I know programming assignment is due for a long time.
Yeah.
Could you put it up?
I could post it already now. I was thinking, so we're going through today's and next and Thursday material. You're going to combine today's and Thursday lectures in the programming assignment. But you're right. I have it, and I could post it just later tonight. Yeah, just so you can start looking at it. But yeah, I guess didn't want people to look at it and say, "Whoa, I don't understand a word," because after Thursday you will understand everything. But basically, just in terms of the planning, after Thursday you know everything you need to know for writing programming assignment 1, except possibly MATLAB programming. So that's the big challenge. But as you see, it's not due until about almost a month from now, right? So But I will post it, so, and we'll talk a lot about it. And after that, it will go quicker. Then it's like 2 weeks between the programming assignments. So yeah, maybe it's a good idea to start early. Yeah. The program assignment, if they need functions? Well, all it has to do is, I will ask questions. Like, typical programming assignment is, write a function, we want to solve this problem. Write a function that solves this sub part of it. See, run it with this and make a plot, maybe. So you're going to need something like Word or something where you can paste in plots and code and stuff to report this. A few sentences usually, say asking maybe like, what happened and why. That's a typical programming assignment. We'll show it, but it's mostly code. It's mostly writing code that works well. That's true. All right.
And inefficient programs will be okay as long as it does the work.
You mean efficiency? Yeah, we'll come to that later. But given that many people haven't even programmed before, efficiency is not. Having said that, if it takes like an hour to run, some things can be really way too slow. It's hard for these programming assignments to make it that bad. But when I taught 128B last spring, we did big systems, and people did things such that it took like 10 minutes to run. And it's just not good for anyone, including the students, because you can't debug it. You don't get. So sometimes performance matters. I don't think for anything we're doing here, performance will matter that much. But I'd like to teach you guys, I love for you guys to write good code, right? And if it takes 100 times longer than it should, something is probably wrong. So we can talk about that. Come to me if your codes are too slow. At least I'll tell you how fast my codes are, and you can try to see why yours is slow. But yeah, as I said, this is not primarily a programming course. Unfortunately, I would love for it to be and emphasize more programming practice, but we have so much numerical analysis to cover. All right. We are here. Busy day today because I want to cover all of it. Maybe I'll postpone some proofs or something for Thursday, given that I'd like to give you enough for doing the homework. Just going through quickly, I think maybe you guys thought that 1.3 was a little abstract, so just a quick run through of that. We talked about error growth stability. This will make much more sense when we actually come to good examples, not just made-up examples that I came up with. But I did say that, you kind of have a feeling for things, there will be errors in what we do, and many methods we deal with will depend on some sort of iteration. So the subindex n here indicate that, there will be one error, and then you work a little harder, and there's another, etc., right? And presumably errors get worse. And if I had an example, but it will come as soon as today's lecture, you will see an example of error growth and how it can go. But I made on the blackboard, I made up some simple examples where you could see an error being 0, and then something, and then something, and something. And I just pointed out the obvious thing, that linear seems kind of bad, but much better than exponential. And of course, to make that precise, it depends on what these C's and N's are, etc. By the way, a good comment last time is, of course, exponential. Exponential can be good exponential if it's exponential decay. So that C is, of course, intended to be greater than 1 in this example, meaning bad exponential growth. So we don't want that. And basically, they define really, really vague definitions in the sense that you can't really look at an algorithm and tell if it's one of these. Some of these definitions are vague. But it's pretty clear from the context that you don't want errors to grow so quickly that it ruins your results. Just a little bit more precise, we can define, for example, something called a rate of convergence of a sequence. So we talked in calculus a lot about the sequence approaching a value. For example, you have a sequence alpha n, an infinite sequence of numbers, and it converges to alpha. And in calculus, we know how to prove that it converges to alpha. And by the way, the setting here is that this is going to be a sequence, hopefully, of errors in a method that you made up. And we want to show that it converges to what number? 0, yeah. If you work really, really hard, eventually the error should get smaller and smaller and approach 0, right? So that's the setting. But it could be used for more things, but that's basically the setting. Now, so we know that alpha n minus alpha is approaching 0 then. And all this is about is saying how quickly, because we want to rate one method is faster than another. And it's really, again, iffy, but at least we can make it precise by saying that if you ignore constants, you can bound it by some sort of expression depending on n. So beta n here could be, and typically, as you see down here, it could be typically 1 over n or 1 over n squared or something. And I had some examples last time showing that obviously a 1 over n square would converge much faster than 1 over n. Again, depending on the constants. Because the idea of this big O notation is that there is a big K that we don't care about. So clearly for certain n's, certain k's, it could be that a linear 1 over n could converge much faster than a 1 over n square if you want a certain precision, right? But eventually, of course, 1 over n square is speeding up. That's what it is about. You have some exercises doing this. It's kind of calculus, just rewriting it in a different form and putting a big O on it. It's extremely convenient. Just focusing on one. If you have something saying 1 over n plus 1 over n squared minus something over n cubed, blah, 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 and you know n is going to infinity. You all know, we play those games in calculus all the time, that the first one is going to be the dominating one, okay? And this allows us to be less precise about it and just say, look, this is ordo. That's in the, it's approximately 1 over n. But it's more rigorous than that. It can be bounded by a constant times that term. So it allows you to throw away everything else to just get a feeling for how quickly it goes. Completely analogous to that are functions. Then, of course, you have a function, big F here, that depends on some h, and it has a limit as h goes to 0. Okay? And that's just like the n previously went to infinity. Now we have an h that goes to 0. And this is a function that has a limit of L. And we want to be able to say, so we know that f of h minus L goes to 0, right? As h goes to 0. But the setting is kind of that small h's are hard. You work harder and harder the smaller h is. So this is, by the way, chapter 5, ODEs, that we're going to use this a lot. So small h means you have to do a lot of work. So the question is, you have two methods. Is one giving a much smaller, much faster convergence of fh to L than the other one. And you do it completely like we did before. You come up with some form, typically h to the power maybe. And your examples in the book that you'll do on this are going to say that, you do some Taylor, you do some cancellations, and you'll see that ordo h, of course, is OK. It goes to 0, but ordo h squared does it faster. Exactly the same thing. That's really it. Those are the slides I had for 1.3. So you see chapter 1, entire chapter 1 is kind of a little abnormal. It's just short IDs and reviews that make sense as we go, keep on going in the course. Anyway, there are a few homeworks on that. So, but this is what we want to do now. Chapter 2. And in fact, I don't need the blackboard for this. So we're going to start talking about solving equations in one variable. It's, of course, the first thing you would start with. And many of you know how to do this. You should have heard about, for example, Newton's method. Newton's method is something, I think they teach you that in high school, right? In calculus a little bit. Or we teach it in calculus, actually. When we in 1B here, I remember teaching it. So you've seen Newton's method. We'll analyze Newton's method. Newton's method is really the king of equation solving method. It's really working extremely well. But we'll set it up in a setting. We'll see some issues with it. In fact, your program assignment is pretty cool because it addresses some of the issues with Newton. But let me first just describe a very simple approach that I already hinted at last time called the bisection method. Okay? So what is this? So the idea of root finding is that, of course, or solving equations. What do I mean by solving equations and root finding? It's kind of the same thing, okay? Root finding is that you have a function, f of x, and you want a root would be where it's equal to 0, right? Now, equation doesn't have to be fx equals 0. It could be fx equals gx, right? But just move the gx over and so it's kind of the same thing. So if you don't mind, I could draw most of my examples as finding zeros, right? So you have some sort of function f of x. And this is what we're after, right? You want to find a good value for that. What do you know? How do you know? Do you know how to do any of this? I mean, if it's a straight line, I mean, you shouldn't use these methods. You should just write down the solution, right? The quadratic formula, you know about that, But, most equations out there, we just don't know how to solve very well. So numerics is really the way this is done in the real life. You want to find that point, you need to do it numerically. And you will find, of course, approximations to it. How do you know it's an approximation? If nothing else, just because the computer, as we discussed last time, cannot even represent all numbers. So suppose that solution is pi. Clearly, you would have to find an approximation to pi. Because our floating point numbers don't even know what pi is, right? But that's OK. But that's a small error. That's something called a rounding error, and it's typically on the order of 10 to the minus 16. A much bigger error might come from you just not solving it well enough. Okay? The methods we discuss now will have something that's called truncation error, so it might actually introduce a bigger thing. So typically, as I said last time, the floating point standard is so successful that most people, including you guys taking this course now, we don't have to worry about it that much. So what we're going to worry about now are the errors we introduce from our methods not being perfect, not the computer. But there are two errors, and it used to be in a few decades ago when these classes were taught, it was really emphasized much more that there's rounding error and truncation error, and sometimes it matters. Anyway, here comes this first very simple, straightforward method. I discussed it before. The idea is the following. Suppose you can give me a number a, x equals a, and of course, here's a function value f of a, right? And then you give me another value b, and here's f of b. What do you know? There must be a 0 in between if the function is continuous. So I mentioned that in many of these methods, we have to assume, in fact, this is one of the least restrictive methods, because all you need is continuity. Okay? As soon as Newton's method, you're going to need differentiability, etc. I discussed that last time. So, but anyway, suppose if it is continuous there in between, we know there's a root. Straightforward application of the intermediate value theorem. Okay? Can we turn this into a method? Well, actually, the problem with the method is finding a and b. Okay? So in your program assignment, I'll show you how one way to do it. But that's kind of an issue. So that's the startup thing that this method does not address. But suppose you have an a and b. Have you solved the equation? Have you found an expression for that root? No, but you have something. I mean, it depends on how far away a and b are from each other, right? So it looks bad here. It looks like, well, you don't know much. But for engineering application, maybe the way I drew it here, maybe this is good enough. Saying that, look, the root is between a and b. I'm done, right? Most likely not. So how can we improve it? So there's a very simple algorithm here of trying to shrink this interval and making sure that the root is still in the interval. How do we do it? So this is the idea. Bisection kind of indicates that you split it in two. So we're going to compute, let me see if I get the right terminology here. Yeah, let me call it the following. So the first interval we have is, of course, that the root is somewhere between a and b. And I'm going to call that a1 and b1. Okay? So a1 and b1 that's the same as a and b. And I'm telling you the root is somewhere between a and b. And if you like it, you can quit. Okay? But let's assume you don't like it. Then we're going to compute a p1. And the idea is that you split it in two. You find the midpoint between those two. Okay? And we call it p1. What do we do with p1? We evaluate f at p1. Okay? And now, of course, you got to choose. You can all see that I want to choose the right subsegment here, right? And what's the logic for doing that? Why am I choosing the right based on f of p1? Because it's negative, right? So I keep the property that one of them is negative and the other is positive. And after this, I can completely forget about this portion here. Because now, to be honest, I might have missed a root here. I could have drawn a case where it did that, and this would still happen. That's OK. This method will not find all of them. It will find one root for you. But anyway, so if I do that, I can just do this and say that now I have an a2 and a b2, where, of course, b2 is equal to b1. But a2 is what we call p1. And this is half the size. Maybe now it's good, right? But of course, the idea is to keep on going. So now you take a midpoint of this interval, and you call it p2. Sorry that this is getting a little too small here. I'll have other demos. At p2, you evaluate an f of p2. And in my example here, it looks like it's positive, which means that you do the opposite. You choose the left subportion of your line, right? Or in other words, you set the new b3 equal to p2. And here's a3 is, of course, the same. And now I'm not going to keep on going because it's getting messy. But it's pretty clear that we will compute the midpoint, 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 and we will narrow in like this, right? And eventually you'll have an a10 and a b10 that are maybe just 0.001 away from each other. Isn't that a cool method? Well, cool or cool, but it's kind of working, right? It doesn't need a derivative. It doesn't need much. In fact, do I even need f of p1? What is it? Only information I'm using? Sign of that. Unfortunately, most functions are such that they're usually not a fast way to just get the sign. It's not like that speeds it up by a factor of 10. Usually you have to evaluate. But anyway, it's kind of good to know that your method doesn't even look at the value, which has a few issues with it. Let's talk about coding. I'm going to write the MATLAB code for this. Algorithm. Let's discuss just how to do it. So a little bit of MATLAB, I'll demo more later, but a function in MATLAB always starts with the word function. By the way, you're putting this in a file that ends with .m, and I would recommend that you call it the same as the function name. So first of all, the function name is coming here, but first of all, you list all the outputs from the function. What do you think is a good output from this function? The 0, right? Or so in my nomenclature here, there are these p's, but let's say just p, right? What you call it is maybe not, well, it is important, but you want to output what the person who calls this function wants to figure out this root, right? So the 0. So let's just say that the output here is p. Then you do equal, and then you do the name of the function. And this is something you just make up. And bisection, I think I called it. And I recommend that you save this in a file called bisection.m. Okay? And I'll show you more with MATLAB later, but let's do it on the blackboard first. Then you list all the inputs. What do you need to tell this function? What does it need to know? A, B, and F. So here are good things. A, B, I told you already. I don't have a good, this method does not tell you A and B. Okay? In your program assignment, we will propose one way to do it. But for now, we don't want to discuss that. So A and B are inputs. When you use this function, you have to give A and B. Okay? Something even more fundamental is, of course, it needs to function. And there is a nice way in MATLAB to just send a whole function in. And it's a little confusing, maybe. How can we pass a function? But that can be done. So it wants the function. It wants A, and it wants B. Can you imagine something else it wants? Error, how close? Yeah, or tolerance, yeah. Some way to tell when do you want me to stop. Okay? And this is a really iffy part of these methods. But for these methods, it's pretty cool, or pretty well defined at least, because we know a good error estimate. If I stop at 3 here, the length of this interval is clearly, what can you say about the root? In fact, if I tell you the midpoint here, I know that it's half of this away. The worst that can happen is that it's half of that width away. So I can give you pretty rigorous. But anyway, the user needs to say, when do you want to stop? And that's usually called a tolerance. So let's call it TOL here. So there is, by the way, methods in the book, the pseudocode. I mentioned I'm not a big fan of the pseudocodes in the book, but you can look, and it's going to be kind of similar. But this will be straight in MATLAB language. And how do we do this?
Output will be an interval.
What?
Output will be an interval.
No, you could, if you want it, you could make it an interval. To be honest, MATLAB is so flexible that I haven't even said what P is. MATLAB is what's called a weakly typed language, that you just make P whatever you want, and it will be whatever you want. So if I want to, at the very end here, I could type, I'm going to erase this, but I could type, when I'm done, a vector AB, and MATLAB will send out an interval, if that's what you want. Then P is a bad name. P indicates that it's one single root, right? And that's what I'm intending. But MATLAB doesn't even know. In any decent language, well, MATLAB is OK, but in a more strict language, you would have to type your P and say it's going to be a double, and then it would be more clear what it is. So yeah, the answer is I intend for it to be a scalar, which means that at the end, you have an A and B that's not a scalar. Maybe I'll take the average or something. Actually, I don't even do that. Oh, yeah, I kind of do that. We'll see what happens. Anyway, control structures. So you know your control structures. If you take an introductory programming classes, they teach you about for loops. That's probably the first one. And then they teach you about something that could be a do or while loop. And the rule of thumb is a for loop is when you know how many times you want to do something. Otherwise, you do something else. So this is a while loop. So in MATLAB, you type while. And now, of course, here should come an expression that if it evaluates to true, it will loop. If it evaluates to false, it will stop. So the right thing to put there is something saying, are we close enough? OK? Now, the CS people here will hate what I'm going to do now, but I just appreciate this short way of programming, putting true here, or 1, which is the same. OK? This is something called an infinite loop. And then I can control where I end later. And I'm admitting that I've taught a lot of programming, and we don't recommend this type of programming. Now, Having said that, it just makes the code shorter, because otherwise I would have to, before I even enter the loop, figure out whether I want to quit immediately. Okay? There's always a few lines of pre-processing that I have to repeat inside, and this is going to make my life a little bit easier. You'll see when I write the code what I mean by that. What are we doing? So you have an A and B coming in. What was given that you have a function and you have A and B, and by the way, there's a requirement of A and B, and a really good code should make sure that you satisfy that requirement. I'm not going to do that here, but you should probably check that f of A is negative and f and B are positive. Or, by the way, what happens if it's the other way around? The method might change a little bit, but is it going to break the whole thing? No. So the only thing I ask for is really that I have different signs. But let's not do that for now. So given that you trust the user that it has this property, the first thing I did was really compute this midpoint, right? So let's do that in MATLAB. And in MATLAB, you just write it out. So let's compute something called a P. And maybe the very first thing for those of you who are new to this that is confusing is that I write these math algorithms, and I don't have a P anywhere here. In fact, by P, I will probably denote the actual root eventually. I call it Pn, and P1 and P2. You could call them that in MATLAB, but if I put P1 here, I don't know if it's P1 or P2 or P3 because it's going to keep on looping. So quite often in a loop like this in MATLAB, we just rename things. And that's often the difficult thing of just taking a math expression. I could write this formula in math when I use Pn and stuff like that. And here I'll just call it P. But it will be pretty easy to understand. This is an assignment. It's not an equation or anything. It says evaluate this stuff here, which is the midpoint, and assign it to the variable P, which actually didn't exist before, but it's not a problem. And now, the way I did it, now is a good time to determine if you want to stop. And it can be discussed. But as I said, I know that the root will be the worst case. If you take my initial A and B, the root has to be somewhere here. So if I tell you that the root is that midpoint, the current value of P, what's the worst I can be? Wrong. It's kind of B minus A, but it's actually better. It cannot be more than B minus A half, right? The worst case, so I'm going to tell you this value now and exit. Well, it could be here, it could be here. So it could only be half of that value. Or in other words, P1 minus A, this is a guaranteed bound. And we can prove that. It's pretty clear from this method. So if you do P minus A, if this is smaller than tau, well, that's OK. If you tell me that you want 10 to the minus 3 accuracy, and that this value is that close to A, then I can quit. Okay, we'll make it more formal. And I'm going to write it like this, break. And this is the type of MATLAB programming that maybe is not so recommended. Instead of putting the termination criterion here, we put it wherever we want and break the while loop. But it's pretty easy to read. While forever, this is pronounced while true or while for loop forever or whatever. Compute a P. If it's close enough, stop. What if it's not close enough? Now comes kind of the main part of the algorithm, namely this little shuffling trick here, right? So what we would do, yeah.
Why would you care about the accuracy on the x interval rather than how close the function's value?
Good point. And when we look at other methods later, I will tell you that you need to care about both. I can give examples where, like you said, x accuracy is really bad. But I can also give you examples that looking at f gives you very bad accuracy in the x. Maybe if I should, so it's not clear. But if I want to make one sales pitch for this method, is that the output is an x value, right? And you as a user, this is actually kind of nice in the sense that you tell me how accurate you want that value, okay? And you're right that f of that value I give you could be 1 million, right? And it could be really bad. But at least I guarantee that I'm just 10 to the minus 3 away from the true value. So in that sense, having a tolerance applied on the x value is reasonable. But in other ways, like you say, you want to make sure that the value of f is very small. Because after all, you're trying to solve an equation. This is an if. This method doesn't do f. You could change it to do that, but it's really the x. It doesn't even, as I said, it doesn't even look at the value of f, right? Just look at the sign. So it doesn't come naturally from this method. All right, so what's the logic here? If this was negative, the logic was kind of we set the new A equal to P because why? Because f of P1 was negative, right? Next step, we noticed that f of P2 was positive. Then I set the new B equals to P. But if you want to generalize that, what I really was doing was that since f of P1 had the same sign as f of a, you could skip f of a. So the new a is p. Now, this one was different, right? So that's really the logic. Then use an if statement again. If, and well, we can be a little sloppy. You can work with signs here if you want to, but why not do this? F of a times f of b. Sorry. P is positive. This is kind of a trick to see. You multiply the function. I mean, this is, if you were doing this by hand, it would be completely insane. As I mentioned, you don't even have to evaluate the function. You just need the sign, which you might be able to do faster. But multiplying them, just to figure out if they're equal signs. That's just me being lazy or something, right? Because you really should say if the signs are equal. But, you know, to turn it into a one-liner, multiply them and see if it's positive. And of course, if the signs are different, this would be a negative number. So if they were equal, then we wanted to set the new a equals to this p, right? Otherwise, which is else, we set the new b equals p. And this is, now you're done. Sorry that I squeezed it in, but I'm going to squeeze in an end here as well, and an end here. And I'll show you the MATLAB code later, when it's complete. So this is kind of short with some ugliness, some tricks. It's kind of nice to be able to see the entire algorithm actually working. We'll run it, and we'll see that it's working. But this is how you do it. So clearly here is where you might make mistakes. This you have to double check. Yeah?
What if you ended up getting a p that was exactly 0 when you evaluated it? Would
Yeah.
you get an incorrect?
Yeah, so I'm not really taking care of that, right? It will pick one of them, right? So that's this is the sloppiness of just looking at the signs. And you might have to look more carefully into that. Although I don't think it will freak out. Because it will assume equal to, since I put greater than and not greater than are equal, and it was not by intention to do that, right? It could be, it's just one or the other. But clearly it would think that they are different signs, right?
Yeah.
So it would move the A up there. And it will keep on going and narrow it down.
Optimize it to make it so that if it guessed a zero, if it happened to get a 0, just return that.
You could do that. It's, you know, by those optimizations look nice, but it's just like, in a real setting, it's extremely unlikely.
Yeah.
Because it wouldn't have, but yeah, you could do those things. But maybe more likely is to, this goes back to the question about why don't we look at the value of f, right?
Mm-hmm. Yeah.
Why don't you add, well, this is kind of nice, but what if f of a is less than some other tolerance, right? Then we end as well. That would cover that case, and not require you to be right at 0. Anyway, this is the whole method. Let's run it. So how do you feel? Was that the first MATLAB program for some of you? By the way, a few comments that are maybe a little freaky for people from other languages. Did you see how smooth this was? This is a function call. You send in a function, and I'm assuming it takes one number and it returns another number, right? And I just send it to A and I send it to P and it returns numbers, right? Now this is kind of nice, and most languages have similar features, although some languages do not. But this is the power. So we're going to send in a function here, which of course, just to use this, we need to work a little bit on how to define that. And I'll show you a neat syntax that we'll be using a lot in MATLAB for doing that. It's, oops, maybe I should, didn't I do that? OK. So, so I post this code on the web if you want to have a look at them. So in this case, so MATLAB, you see my MATLAB? Big enough? Can you read that? Yeah, you'll be fine, right? Otherwise, I'll make it bigger. So this is MATLAB. Hopefully, many of you have started it already in section or something. You have a working directory where you put your files. And the way we'll do most of this is that you just put all your M files there, and it will find them. But it can be discussed exactly how to do that better. If you want to look at my bisection, you could do type bisection. Of course, this you have to download from the course webpage. It's not part of MATLAB. It's something I wrote and put there. But you could do that on any function. Well, apparently, I forgot to download it. Actually, I didn't, but I think I saved it at the wrong place. Didn't I download it? Downloads. How does this work? Oh, I messed it up. I thought I did. All right, let's see if we can get it from here then. Oh. Crap. I would like to, yeah, I need that AT&T sometimes. That's why I don't kill it. All right, now. Lesson for the future, don't suspend in between. Because I kind of did this before. All right, now where were we? We were, wrong class. Here we go. All right, there, I put them on the desktop. Okay, good. I did download them. I didn't want that, but that's OK. Bisection. OK, so here's the function I just coded. And it's identical to what I wrote, I hope. Yeah. All right? So that's the function. How do we use it now? We're going to call it. And the way you call it is almost identical to the first line. But of course, you have to replace f, a, b, and tol with what you want. And you don't type the word function. Let me first tell you how to define functions in MATLAB. A function can be defined as writing another M file, and it's what I recommend in general. But for really quick things, it's actually kind of nice to just use a syntax that looks like this. You might have seen it before. It's just something called a lambda function that they have introduced recently in MATLAB, or maybe 5 years ago. But you just do that, and you can type an expression. So what can we solve? We can solve, what do you want? The square root of 2, right? How about that? So f is now a function. And that's how easy it is to do this in MATLAB. Now, of course, you need a's and b's and tols, and you can just send them in directly. If you have started with MATLAB a little bit, you know that everything is assumed to be vectors. So it's not just scalars. In this function, we'll just use them as scalars. But suppose I want to plot this function. Then the way you have to do it in MATLAB is to turn it into a vector. And you will learn, maybe if you do the very first slides of any tutorial of MATLAB, you'll see that we actually prefer to put dots in front of many of these operations. And it's something I don't appreciate with the MATLAB design. I think it would be better to have special cases for the matrix operations. But this is how it works. So you'll see if you run into this problem. It will give warning messages or errors if you do it wrong. But I'm going to do that for now, and you'll see later why. It's because I want to be able to send in vectors. So now you can do f of 1. And the answer is, of course, going to be 1 squared minus 2. Right? But because I put the dot there, I can also do this. And it will do 3 values at the same time. It's called vectorized operation. And while maybe a little weird, it's one of the reasons that MATLAB becomes extremely easy to use. How can I plot this function? And I can tell you, MATLAB doesn't know much. It doesn't know how to plot functions. There are some functions, but by default, people don't use them. It only knows how to draw straight lines between points. Can I use what I just did? Yeah, if I draw straight lines between 1, comma, the first value, 1.1, comma, the second, etc., I will plot the function, right? So the way you do this is that you create an x-axis, let's say 0 in step of 0.01 to 2. And now you can plot x versus, or f of x versus x. And there is the function. OK? That's how MATLAB goes about plotting functions. So you'll be doing this a lot yourself. And I'll come back to it later. Is this a good function to try to solve for a root? Yeah. It crosses 0, right? But you have to choose a and b. What are good a's and b's?
0 and 2.
That would work fine. Good is a relative word, but it works, right? Because f of 0 is negative, and f of 2 is positive. So that works fine. All right? So now we can say bisection of this function, 0, 2, and we need to tell it when to stop. Let's do this. Let's go slowly here. And you run it, and it will terminate with a number, p, that hopefully is pretty close to the square root of 2. You can, of course, check it. OK? Do you think MATLAB is only calculating with 4 or 5 digits? I did this last time, right? Format long. It assumes you don't want to see more. But you can see that these two values seem to differ somewhere here. That's a 5, and that's a 4, right? But indeed, the difference is less than 1 10 to the minus 3, which we asked for. So it really did what we asked for. Why not just reduce that number? It's a computer. Now it seems that we're matching up to that digit, which is about 10 to the minus 8, right? So it seems to work. Wouldn't it be nice to see all those intermediate values and see what it's doing? Well, it depends on what you want. If you're giving this to someone to actually use for solving for roots, they probably don't want to see the internal details. At some point, you want to turn a function into a black box and just say it works. I'm happy, right? But when you develop methods, you want to see more. And I recommend this when you code yourself. So I put a function on the web called bisection_table. Okay? Let's look at it, not edit yet. So this is the same function, but I padded it with a lot of stuff that looks cryptic, but it's only printing. Okay? So like bisection, this is a comment, by the way, but it's printing a convergence table. So it's going to print the n, the step, the a, the b, the p, and the function value. And every time you take a step, it prints all those numbers. So it's going to return. It's going to work exactly like before, but printing a bunch of stuff. Let's do it. We want to see it now because we're studying the method. And we can get a bunch of information out of this. All right, so a and b were 0 and 2, because that's what we gave it. And p, remember, we decided p is the midpoint. That's just not really part of the method, actually, but it's going to be part of the next step of the method. F of p is negative, so what do? We set a equals to the new p. So now it's 1, 2. We zoomed in on 1, 2. And then the next step, you zoomed in on 1, 1.5. And you keep on going, and we actually ended up having to take 27 steps to get the accuracy we wanted. And by the way, here we're monitoring the fact that we're really solving the equation pretty well with that stuff. Okay? This is not rocket science. This is a pretty straightforward method. But if it's the first time you see MATLAB, it's kind of nice. There are some benefits with this, namely that it's kind of guaranteed to work. Other methods we look like have all type of issues. And this method might not be fast. There are some issues. But it's really, if you give it an F and A and F and B that are different signs, it's really going to work. And that's one power of it. What else do I want to comment on? Let's try something. Well,
What would happen if you didn't have this line while 1 in this?
if you take this away,
Yeah, like what is the
well, then you have to take away this as well, because you can't break unless you have a while. But it will basically do it once. It will take one step, right?
we can do something like p is equal to this and then if and
Then end, OK? But somehow you got to get back here and repeat. And the way we do that is a while loop, right? All languages had goto. Remember goto? You could say go back here. But while loop is better. But that's kind of what I'm doing. You want to repeat somehow. And we don't know how many times. Yeah? Multiple roots. That's a good question. So what do we do then? Let's do f equals, this is a great multiple root thing, right? All right, well, what will the method do? First of all, are my a's and b's good? A little iffy, right? It's equal to 0 on one of them and positive on the other. And we discussed that before, and it's the case I didn't really, you should address it in a real code. But let's just avoid it by now by changing it to cos. Now are they good? Still not good, because now they are both. So remember, we're looking at f of 0 and f of 2. And in order for this method to work, they have to be different signs. And they are not, because they are positive, both of them, right? Yeah.
Why don't we just change the A and B instead of changing the function?
To change your what?
Why don't we just change the A and B?
Yeah, we could do that. So what's a good b then? Well, something here, right? 1.6 seems to work. Let's do that. Now, what root do you think it's going to find? There are many roots in there. I mentioned before that if this function did this, there would be 2 roots here. And it would do exactly the same thing as here. Namely, ignoring those 2 and finding this guy. So is there a pattern? Let's try it. So as we said, we want to do this guy, but we have to change this value. And let's just not go so far just because it's a waste of time. Well, it found this guy, 0.157. Why? It's kind of weird, right? You see a pattern? Well, it's kind of tricky. There is no clear pattern. It depends on how these midpoint signs end up working out. You can just do it by hand. In fact, if you look up here, you see that it ended up making a decision to skip the whole right end, and then it skips the whole right and the whole right. That's what it ends up doing. So it's kind of random. If you move this 1.6, I'm sure 1.5 is fine. It ends up finding a different one. In this case, it found that guy, right? So it's kind of random. So that's the issue with this method. It finds one root in that interval. You're guaranteeing that there is at least one, and it's finding one of them. All right, what else is there to say about it? Let's see in my slides. Here's the method described in words, but it's exactly what we just did. Here's the code. Yeah, we talked about how to stop. What am I doing? I'm kind of doing the first one here. Yeah.
This probably will be on the scope of what we're doing right now. We're assuming that these functions are continuous.
Yep.
Would there be a way to algorithmically check whether a function is continuous on an interval or not?
No, that's symbolic algebra. You give me the functions here in MATLAB are procedures in the sense that you send in a number, they do stuff, and they return a number. So all you're kind of allowed to do is to send in a number and look at what comes out. And you can plot it like we did and say that, well, it looks continuous, but that's not a proof in any way. It's really just, no, I would say it's impossible, because I can come up with crazy functions such that you will never, if you give me an algorithm that you're testing points and stuff, here's the function, I could take x squared, I could take this function, super smooth and nice, and then I define a new function such that at one point that you have no idea what it is. Let's make it pi. It's undefined, or makes a jump, right? So no, it's you have to trust the user on this one. Termination criteria we'll come back to later. Overall, it's not that much of a big deal in this class, because it's an iffy business. We can't say many absolute statements about it. But in practice, you have to deal with this if you wrote a good code. Can you make a theorem about how quickly it converges? It's kind of easy, right? Everything is kind of simple. We split it into, so what's the guarantee? I told you already before even doing anything, based on your input, if I tell you the midpoint here, I have found the root with an error of half of the interval, right? At most. That's kind of not doing anything, just computing that p and exiting immediately. I've given you an error of half your interval. Presumably, you're not happy with that. I'm just saying that's what I've done. How does this improve for every step? 1 over 2. I divide it by 2 every step. That's how simple it is. Turn it into a theorem. It says that, so the left-hand here, you're going to see a lot of these things. P in this case is not my p. This is the true root. In math notation, we like to put a little index for our iterations and take it away for the true answer, just like I did with alpha n and alpha before. So this is the error at step n. And it could be 0, it could be anything, right? But we're guaranteeing that at the first step, it's b minus a over 2. At the second step, it's b minus a over 2 squared, etc. We divide by 2 every time. Isn't that nice? So what's one typical stupid homework example that you're going to do with this? Before you do it, you want to determine what? Yes, exactly. That's a typical stupid homework problem. So go ahead and have fun with that. And you can see how to solve that equation. But then you can determine that, before you start, you know how much work you're going to have to do in order to solve the equation. What do we call this convergence in terms of rates? Well, b minus a is a constant, right? And it might matter a lot. But remember, rates, we just ignore that. So this looks to me a lot like order 1 over 2 to the n. And it's actually not the example I said before of n to the power of something. It's 1 over 2 to the n. So that's a way to describe how fast this method converges. And it's not that fast. As you saw, I needed 27 iterations to get 8 digits, right? That's for the obvious reason that 2 to the minus 28 is 10 to the minus 8. That's OK, but Newton is going to do this in 3 or 4 iterations. So, we'll do better. I'm not going to bother proving that theorem because it's so clear from the picture. OK, is that clear? Bisection, you're all happy with it? Yep.
Sorry, I don't know whether you know whether or not this is true. Calculators, on my calculator, you do a left guess and a right guess, and you can guess a 0. Is it
OK.
using this algorithm?
Well, I don't know, but no, most likely not. But it might use a combination not too different from what you're going to do in your program assignment 1. But most likely, they don't like to take derivatives. So I'm talking so much about program assignment 1. I should have had it up. You're going to do kind of this, but then if you can, you're going to do Newton. And Newton, you've all seen, it needs derivatives. Calculators don't like derivatives. So I think they do something called the secant method, which we will also cover. A combination of this and the secant method. Or there are various variants like that. Because speed is not that important. But they can, yeah. But since they want, so they really want 2 points, and you're telling it that it's an upper and a lower bound.
Yeah, you give a left guess and a right
Well, they're doing these tricks for sure, in order to guarantee that it finds it. Yeah. Good comment. What is that, like a Texas Instrument type thing?
TI-83. I've
Yeah.
done all the 80 series.
You can't bring that to the exam. Good. That's cool. Anyway, let's find better methods. Fixed points. So speaking about calculators, back in the old days when calculators were simple, you type a number, and then you press, for example, square root, or let's say cos, and it took the cos sign of that number, right? While, of course, calculators today look more like MATLAB, that you have to type cos of a number, and you get the answer, right? Now, I don't know if you've been so bored sitting with an old-time calculator in front of you, but I have, that you try to just press cos many times. Have you done that? I don't know if it's interesting. Unfortunately, I can't read. Oh, maybe I have one of these Windows things here. Oh, there's a calculator. But there's no cosine. Wait, they have this here. Scientific. All right. So you type something. Oh, by the way, degrees, this is not good. We don't like degrees. Radians. OK. So you type a number, let's say 1, and you press cos, and it takes the cos of that number, right? OK? And then you're so bored, so you keep on doing it. Have you seen this? I wish I could hold it down. What's going on? This is what we call convergence, right? Or at least apparent convergence. But we'll prove it. It seems to, a lot of digits here. But it seems to converge to a number. And it stops changing. If it stops, what is true about this number? If this is x, and I press cos and it doesn't change, then cos of x equals x. I solved an equation. I solved cos x equals x, which is non-trivial. The only reason it worked is that it was written on the form x equals cos x, right? And by the way, there are other reasons it works. There are other forms that wouldn't work. But that's kind of interesting. This is called a fixed point iteration. Fixed point meaning that it finds a point x such that when you apply the function cos, it ends up where it started. Okay? So we really solve the equation x equals cos of x. And this is the basis for many, including the famous Newton method, for understanding it, to see what's going on here. It was clearly an iteration. We had to keep on stepping. But just to show some other things, why wouldn't I be able to do inverse? Do I have inverse cos here? Inv. There. Oh, this is going to take forever. But by the same argument, this number, if I take inverse cos of it, of course, it should also return x. And indeed, it did, right? You see that? No, I haven't tested this. There's a reason I keep on doing it. Look at the 7 look at the very last digit. It's doing weird stuff, right? I wish I could do this faster. Of course, I could switch to I could switch to MATLAB. But you see something happening? Yeah, this is going to take forever. But you see that every time I do this now, 3 digits are being changed, right? Well, it's going to blow up. So how do we do this in MATLAB? We do x equals 1, and we do a for loop, right? 100 times x equals cos of x. And we're not printing it. And there you have the numbers, right? And by the way, I like this format compact. So here I did the same thing. Now let's run the same thing with, it's called arccos. No, it's called acos. Well, it went bad. So it started off at the true solution. I took cos inverse, and of course it gave me the right answer, but then it starts wobbling a little bit, the last digits, and it's blowing up. You see that? And now it's, every time I take a step, changing somewhere in the middle. You see that? And eventually it's really changing the number quite fundamentally. Yeah, now it's complete garbage. So that didn't work. How do you explain that? You would have guessed, based on my first experience, that if you have x equals something, and you just keep on doing something, it would find a root of x equals something of x. Right? But no, it worked for cos, but not for arc, for the opposite. Another fun thing you can try is the square root. What happens if I do square root a lot of times? Where is my square root? There's a square root. That's the third cube.
To the right.
Oh, they hit it up there. All right. What will this converge to? 1. All right. For the very reason that square root of 1 equals 1. It's a fixed point to the equation x equals square root of x. That works. If that works, I should be able to do square, right? Because 1 is also equal to 1 square. So x equals to x squared. So let's do squares instead. Well, that doesn't work. It blows up. In fact, it won't work wherever you start, right? So some things work and others don't. Oops. So if you want to figure this out, we have to analyze it. These are called fixed points. Let's see what we have in the slides. Fixed point, a number is called a fixed point for a given function g if g of p equals p. Okay? Note that this is not solving the equation g of p. This is not root finding for g of p. See that, right? Root finding would solve g of x equals 0. But we're finding g of some p equals p. But it's very related to root finding, that if you want to solve some root problem, you can make up a fixed point by just doing x minus f, or actually any multiple. And you can also go the other way, that if you have a fixed point, then of course you can create a function which is x minus. So what we actually solved was not cos of x equals 0. We solved x minus cos of x equals 0. So fixed points are not root finding problems, but they can easily go back and forth. Okay? So if you can solve, so it looks like maybe we can turn this into something general. That's the idea. Here's a theorem. We want to be able to understand what just happened. Okay? And this theorem tells a lot about that. Okay? It says that you have this g, and it's defined and continuous between a and b. Do you know this notation? Continuous between a and b. Now, what do I say here? I say that if you plug in an x to g, and the x is between a and b, what comes out is also between a and b. That's more restrictive, right? This is not true about many functions, or if you just make something up randomly. Then it has a fixed point. So let me draw the figure in order to try to explain this. What I'm saying here is that you have your cos. Let's do the example we did. Okay? So we had 0, let's say we have 0 here and 1 here. And remember, this converts to something like there, right? So there is our fixed point, where this is equal to x. By the way, what is a great function to draw as well here, if I want to look for fixed points? B over a, I'm thinking much easier. I'm looking for x equal cos of x, right?
Oh, sorry.
Yeah. So no, just y equals x. So this is really the equation I'm solving, right? And this was y equals g of x, which in my example was cos. Okay? Now, it worked in the sense that we started at 1, and we ended up finding that point. But let's see if we can use this theorem. It's saying that you need an interval a and b, and you can make it up, but 0 and 1 are going to work fine. Okay? Now, the function is continuous in that interval, right? It's continuous everywhere, so it's fine. How about the second requirement? If you plug in an x between 0 and 1, do you get a number between 0 and 1 back? Based on that figure, you see that that's the box to draw to show that? Are you convinced that if I plug in, what I'm saying is that cos of x is between 0 and 1 for x between 0 and 1. From this picture, I think I can convince you. It's not true if I go up further, because then it will go negative, right? So it happens to be true here. How do you prove that? Didn't we talk about the maxima and minima in chapter 1.1, review of calculus? Look at the endpoints, look at the derivatives. Okay? So just to show, what I'm trying to show is basically existence of fixed points for this example, where g of x is equal to cos of x. Okay? I'm proposing a equals 0, b equals 1, and it might not work. In your homework problems, you're going to sometimes come up with these numbers. First of all, I need to show continuous. Fine. G is continuous there, so that's easy, right? Now, I'm claiming that g of x stays between 0 and 1 if x is between 0 and 1. And I prove it by saying g endpoint is 1. G at the right endpoint is cos of 1. And I don't really care what it is, but it's positive. It's, you know, it's positive, but it's also less than 1, right? Or let me just say, in 0 and 1. I need to check one more thing, that it doesn't go up. If it did that, it wouldn't work, right? But again, it's from the optimization, from finding the extrema. You have to look at derivatives. So g prime of x is equal to minus sine of x. Do we have any stationary points in this interval? We actually have one right there, but not in between. Okay? So what it's telling us is that, so it's not equal to 0 for x in, let's say, excluding 0 and 1. Okay? So what is the conclusion? I have a stationary point here. I have a left endpoint. I have a right endpoint. I know that the maximum and minimum of this function must happen at these 3, or actually just 2 points, right? And those points are equal to 1 and something between 0 and 1. You see that that's a proof of the condition here. So that gives us that this function is between 0 and 1. All right, what does the theorem say? Then G has a fixed point in A, comma B. All right, so we're going to prove this next time. I'm going to focus on the example first because I want to finish that up so you can get started on your examples. But is this obvious to you guys from the drawing? From this box, it should be pretty clear. I'm saying there's a function existing that is defined all the way from here to there. Okay? And it never goes outside this box. Doesn't it seem like it really has to cross the line y equals x in going from here to there? That's it. What theorem do you think we're going to use to prove that? It's not immediate. It's not trivial. But it kind of has the flavor of one particular one. Intermediate, yeah. It's just that you kind of have to subtract away this x, but it's really intermediate value theorem. In order to go from there to there, and if it's continuous, it has to cross it. Anyway, let's move on and see. This doesn't explain much. This just told us that we have one. How about uniqueness? I have a b part, and it's saying roughly if the derivative is less than 1, it's also unique. Why do I care about unique? Well, sometimes we want to know if there's more than 1, but most importantly, there's a theorem coming soon telling that these iterations converge, and it needs the same condition. Okay? So can we prove using this theorem that the fixed point is unique here? You have to just look at the derivative. Uniqueness of fixed point. Again, g is equal to cos? Well, the theorem tells us to look at the derivative. And it exists and it's happy. In fact, we already did look at the derivative. But let's do it again. So the absolute value, let's just do what the theorem tells us to do, equals absolute of sine x, which for this interval is really just sine x. Is that less than or equal to k less than 1? Yeah. It is an increasing function. Let's look at this derivative. It's absolute of sine x from 0 to 1. That's what it looks like, right? Strictly speaking, you really have to show that is less than 1, k equals, or not k is not equal 1, but here's a 1, right? And you have to show that less than that. But it's an increasing function, so I would say that this is less than or equal to sine of 1, which is strictly less than, some k is strictly less than 1, which means that there is a k less than 1 that would satisfy the theorem. In order to really prove it, I need to take one more derivative, right? I used an argument, I said it's increasing, right? But I'm getting tired of derivatives here. I'm just saying, for your problems, you really got to do that. You got to prove that this function, it could be that it's going up and down. But it's really straightforward. It's just going back to extreme values of function. In this case, it's the derivative, okay? So it tells us that the fixed point is unique. And we prove that too. Can you just look at it and see that this makes sense, this theorem? I like to see, make sense of theorems before you do anything. So the derivative is less than 1. I'm claiming you can't have more than one fixed point. And the way to understand this is, of course, contradiction. Try to do it. Try some other function that has more than one fixed point. Do you see that it then, this is a proof by contradiction. Do you see that then that function must have a derivative that is greater than 1, basically, right? Or equal to. What theorem do you think that is? I mean, so just intuitively, it means that if you cross this guy once, in order to cross it again, you must at some point have a derivative that is more than y equals x, right? To get back up. What theorem do you think we're going to use for that? That's the mean value theorem. And it's not immediately clear. I'm just saying it's the flavor of that. And we'll do the proof next time. It's nice to see. Yeah.
What part of the B in the theorem says that we have to check that the derivative is increasing?
The part of B says that you need to tell me that for all x in A and B, the derivative is less than a number less than 1, right? Which means that you're really maximizing a function. So for all I know, sine could go above 1 and back there. All I did was to say that it's less than 1 at the right-hand point, and it's less than 1 at the left-hand point. But again, there's a derivative of the derivative, a derivative of this function, that could have extreme points. So you got to show, it's really a Math 1A type exercise. I have a function, and it's sine, right? G prime. And I wanted to prove that it's between 0 and 1. Yeah, in this, that's why I'm being sloppy about it. And I could have done that maybe with the cos too. But you realize that if I increase the interval to 0 to 2 or something, things are going to go bad. Because then because it will go, things can go bad for other functions at least. So you have to be careful about it. Anyway, I'll prove those things later, but this is kind of a nice theorem. But I want to go back to the fixed point iterations. So far, I haven't talked about iterations at all. I haven't explained anything about that experiment we did. I have just talked about the existence of fixed points. Fixed point iteration is what we did on the calculator. Okay? It's a procedure where you guess a starting point p0. Remember, I think I did 1, except for the squared example, then I did 7. Now you produce a sequence of p sub n's by simply evaluating g. You see that this is what I did in the calculator? I have a p, let's call it pn minus 1 or p0. I evaluate the function, and that's my new p. In MATLAB, I only called it all p or x or something. And in the calculator, you didn't even see it. It was just there all the time, right? But this is what I was doing. I said before that if it converges, clearly it must be a fixed point. Is that easy to prove? Well, if it converges, it has a limit p, right? So p is equal to limit of pn. Well, pn is g of the previous p. Okay? And if you assume the right things here, you can bring out the g and do the g of the limit of the sequence Pn. But that was, of course, the limit n to infinity doesn't care if you give it Pn minus 1 or Pn. It's still equal to P. So P ends up being equal to g of P. This is something, I mean, this is just a formal way to prove what you had a feeling of, that when I ended up doing it, if I have a number, I do cos of it, and it stays the same. It seems like I have some, I didn't take the limit to infinity, but basically I found a root to x equals cos of x. Do you want an actual MATLAB function? These are the type of functions I recommend that you don't really use mine, you write your own. But if you really want to do it, we need a loop. We're doing something many times, we don't even know how many times. And I would suggest a structure very similar to before, a while loop where you just do p equals g of p0. Why don't I do p? Why don't I just type p equals g of p? Remember in MATLAB I did that. Did you follow me on this one? I just typed x equals g of x. What is the only reason I'm not doing that in this code? I want to, exactly. So I need to know how far it went, because this is, again, termination on this is not clear. How do we quit? Now we don't even have an A and a B any longer. How do I quit? One way to quit is to say that when you took a step, it didn't move very far. So that's what I'm doing here. Let me move on to the nice theorem that I like to show here, because this is a fixed point iteration theorem that tells you everything that we did in our experiments. So it's easy to confuse the conditions here because they are almost identical to the uniqueness. Again, we have a g. Plug in things between, and we have a g and we have numbers a and b. You plug in numbers between a and b and it stays in a and b, exactly what we did before. The g prime condition is exactly the same as in the uniqueness, namely roughly less than 1. But it can't even be equal to 1. Okay? Then the theorem tells you that wherever you start in this interval, the sequence defined by this, the fixed point iteration, converges to the unique fixed point between a and b. Okay? So we have everything we need, right? Don't we? Do you see how it's working out for this guy? We did prove, of course, that it was continuous and that it had a derivative that was, well, slowly. We proved that it was continuous and that it stayed between 0 and 1. We proved over there that the derivative was never even approaching the value 1. Seems like wherever we start in this interval, this proves that it will converge to this point, which is the unique fixed point. Okay? And next lecture, again, I show this proof. It's just a few lines. It's very easy. But now let's see if we can understand why the other ones didn't work so well on that. Let's do another example. Let's do the square root, for example. So square root. Oh, I have the light. It's just that that thing is hiding it. So g of x equals square root of x. Let's see if we can work that out. It might help to do one of these drawings. And you know already, by the way, that the solution is there. What's a good A and B?
1/2, 3/2.
Good suggestion. That's very good. Do you see why I can't do 0? That is another fixed point, and the derivative is definitely not less than 1, etc. In fact, your half here, that's going to be fine. What is the derivative? 1 over square root of a half. Yeah, you'll get away with that, it seems, right? Yeah, good, of course, because it's, but you can't go too close to here because of the derivative condition. You got to choose an A and B, and I think in your homework problems you have to do it. Let's try that value. Let's try a half and 3/2, a nice little box. I need to continue here, but it's basically something like this. Okay? So we have a suggestion for A and B. Our g of x is equal to square root of x. And in order to do this, we have to show all these things. Continuity, check, right? Maybe the big thing is, does it stay between a half and 3/2? Okay? So based on the picture, it seems to do it, but g of a half is equal to square root of a half equals 1 over square root of 2, right? Is that between a half and 3 halves? Yeah. So that's definitely between a half and 3 halves. Good. How about the other one? Well, you can kind of see it immediately from there, right? But you can evaluate it, and that's definitely also in here. Plus, I need one more thing to say that it stays between that value. Check the derivatives, right? But for now, let me just say increasing, meaning no zero derivatives, right? Means g of x is in a half and 3 half for x in a half and 3 half. That's how annoying these exercises are. Okay? And what if I give you a function that is not increasing? Then you have to differentiate. It can be a mess. I think some in the homework might be that bad. All right, so we know it has a fixed point. Next part, is it unique? G prime equals 1 over 2 square root of x. Okay? This function is decreasing, right? So let's just look at g prime at the left endpoint, which is 1 over 2 square root of a half, which is 1 over square root of 2. That looks like it's definitely less than 1, right? Let's look at the right endpoint. Well, let me just say that it's greater than 0 and decreasing, right? You see that that's all the information I need? So the derivative starts off, well, you don't trust me. X is 0.5 to 1.5, right? We're dealing with this function, right? We're plotting it alongside with y equals x. Now we're plotting a derivative, which is 1 over 2 square root of x, which looks like that, okay? What you have to show is we already did show that the blue line is between a half and 1.5, which we did. Now I got to show that the red line, not the same thing, right? I got to show that it in absolute value is never equal to 1, okay? So what I'm showing is that the left endpoint is less than 1. The right endpoint is you know, it doesn't cross all the way down to very large negative values, plus decreasing, which leads to the fact that g prime of x is less than 1 for the x's in this interval. What do I have then? That's all I need. It shows that any x in this interval, in fact, I started with 7. So actually, my little test is not covered by what we just did, right? Because the p0, all we know is that if you start between 0.5 and 0.5 and 1.5, it will converge. But of course, you can do this study for 7. What do you think is going to go wrong if I do x squared? Will it still have a fixed point in this interval? Will it be unique? It's kind of x squared is really just flip mirroring here. It actually happens to be unique in this box still, although the theorem wouldn't tell us because the derivative is greater than 1. But this theorem would fail because the derivatives would be greater than 1. I'd like to do it, but I don't have time. But with this, we can analyze fixed point iterations. That's the idea. All right, anyway, I'll see you in office hour. I have these office hours for the other students now, but if you're desperate, you can come and ask something. Otherwise, I'll see you tomorrow. Thank you.